Hey everyone, just a quick video on Chapter 17, Temperature and Heat, discussing important formulas and terms in this chapter. Okay, let's start off with Section 17.1, Temperature and Thermal Equilibrium. Three important terms in this section. The first one is isolated system, and that means no heat transfer crosses the system's boundary, or that the system is fully insulated. Okay. The second term is conductor, and that is any material that transmits heat or allows heat transfer to flow through the material. And lastly, thermal equilibrium. That means two systems have equal temperature, and that is achieved when two systems are in thermal contact over a long period of time. Okay, moving on to 17.3, gas thermometer and the Kelvin scale. There are two simple formulas that are important in this section, and that is the formula that allows you to find temperature in Fahrenheit given the temperature in Celsius and vice versa. And the second formula is finding the temperature in Kelvin when given the temperature in Celsius and vice versa. Okay, 17.4, thermal expansion. There are three important formulas in this section. The first one is linear thermal expansion, and that is given by change in length is equal to the coefficient of linear expansion multiplied by the original length multiplied by the change in temperature. One thing to note is that the coefficient of linear expansion depends on the material, and that's either given to you or you might have to find that in a chart somewhere. So we can see there was an initial change in length. We're looking at this drawing right here. There was an original length, not change in length, sorry, an original length of a material, and that material experiences a change in temperature. And as a result of that change in temperature, the material either expands or contracts, and that is the delta L here in green. Yeah, and so you could find delta L using this formula right here. Okay. Second formula is thermal stress, and that is equal to negative Young's modulus multiplied by the coefficient of linear expansion multiplied by the change in temperature. And that is, so the stress experienced by a material due to temperature change can be found using this formula. I believe Young's modulus and coefficient of linear expansion, those, like I said, should either be given or you might have to find that on Google or in a chart somewhere. And the last formula for 17.4 that I found important is volume thermal expansion. And that is very similar to the linear thermal expansion, the first formula, except that now we're working with 3D. And this is now in 3D, right? This is not in 3D. This is not in 3D. This is in 3D. That's volume. So that is a change in volume is equal to the coefficient of volume expansion multiplied by the original volume multiplied by the change in temperature. So that is a change in volume of a material due to temperature change. Okay. Next, we will move on to 17.5, which is heat. So we know the conservation of energy, that's work done on the system by an external force is equal to change in potential energy plus change in kinetic energy plus change in thermal energy. But because we are in thermodynamics, we now include heat transfer into that equation, which is symbolized by the capital Q. And heat transfer is the energy transferred between objects which are at different temperatures. For example, there's liquid water, and we put that in thermal contact with ice. Because they are at different temperatures, meaning liquid water having a higher temperature than ice, heat is going to be transferred from the liquid water into the ice. So heat transfer occurs between the two systems, ice and liquid water, because they're at different temperatures. Important things to note about heat transfer is it is positive for heat going into the system and negative for heat going out of the system. Okay, so in the case of liquid water and ice, if we're talking about ice, heat goes from the liquid water and transfers into the ice, so the ice experiences a positive heat transfer. Excuse me. And for the liquid water, it gives off its heat to the ice, so heat is going out of the system, meaning out of the liquid water and into the ice. So for the liquid water, it experiences a negative heat transfer. And heat transfer the unit for that is joules. Okay. So now that we know the term heat transfer, and we're in thermodynamics, obviously, so we're gonna add that into the conservation of energy in this formula. And what we get is this formula, which is heat transferred into the system plus the work done on the system by the environment is equal to the change in potential energy plus change in kinetic energy plus the change in thermal energy, right? But we don't worry so much about change in potential energy and change in kinetic energy in thermodynamics, so let's just cross these guys out. And what we're left with is the first law of thermodynamics, which is this, and that is the heat transferred into the system is equal to, the change in thermal energy is equal to the heat transferred into the system plus the work done on the system by the environment. Okay, that's this guy. So if we're doing heat transfer and temperature change, we're not applying any external work or physical forces to our system. So actually, we could also cross this out, the work done on the system by the environment, right? Because we're not applying any external work or physical forces to our system. So now what we're left with is Q, right, or heat transferred into the system, is equal to E subscript TH, which is change in thermal energy. And another way of writing ETH, or change in thermal energy, is MC delta T, okay? Should know that. And that is mass of the substance multiplied by the specific heat multiplied by the temperature change is equal to the change in thermal energy. So we could see that here, right? You go from that formula to that. So Q is equal to MC delta T. Specific heat that is dependent on the material. Yeah, so we've got this formula right here. This is important. That is how you calculate the heat transferred into the system due to a temperature change within the same phase. Okay, that's very important, that it's within the same phase. So it's got to be either temperature change from liquid to liquid, so it doesn't ever change to gas or solid or anything along those lines. So it has to be within the same phase. That's an important part here. Okay. If it does change phase, let's say it goes from ice, which is a solid, to liquid water, which is obviously a liquid, then this formula right here is not going to be complete, because this is only for the heat transfer due to temperature change within the same phase, but we also have to take into consideration heat transfer due to temperature change as it changes phase, right? So heat transfer necessary to change phase. So we'll talk more about that shortly in 17.6 actually, which we'll talk about right now. So 17.6, calorimetry and phase changes. So here we're gonna talk about heat transfer necessary to change phase from solid to liquid. You see that we have to melt or boil from liquid to gas or vice versa, right? That that phase change needs to occur, meaning this melting or boiling. So in order to find the heat transfer necessary to change phase, we have this formula right here. Okay? And that is plus or minus the mass of the material multiplied by the latent heat of fusion, or plus or minus mass of the material multiplied by the latent heat of vaporization. And the only difference is these two guys, right? It just depends on, are we going from solid to liquid and liquid to solid, or liquid to solid, then we would use latent heat of fusion. If we're going from liquid to gas or gas to liquid, then we would use latent heat of vaporization, right? So whenever we go from solid to liquid, here, we would need to use latent heat of fusion. For this part, when we go from liquid to gas or gas to liquid, we would need to use latent heat of vaporization. Okay. So that is that. And another important term, calorimetry, that is the heat transfer between two systems in thermal contact. It's kind of shown in this drawing right here. And things to know about that is heat flows from hot to cold until thermal equilibrium is reached, or that they have the same final temperature. And we discussed that earlier with putting liquid water and ice in thermal contact, right? Heat flows from liquid water to ice because liquid water right here is at a lower temperature, or is at a higher temperature than ice, which is a solid right here. So heat would flow from the liquid water to the solid ice. Okay, don't want to make a mess of my notes. Okay, the other important thing to know is that heat out of one system is equal to the heat into another system, or QB is equal to negative QA. Whatever, remember, positive and negative, that just means heat going into the system, heat going out of the system, right? So what this means is for ice and liquid water, just because let's use the same example. Whatever heat that liquid water gives to ice is equal to the heat going into ice from the liquid water. So QB equals negative QA. All right, and in calorimetry, the sum of all heat transfer equals 0. And that's this guy right here. That's this formula. So basically, the sum of all heat transfer, it's going to consist of two things. It's going to consist of temperature change within the same phase, right? So let's say this is solid, liquid, and gas, right? So this is solid to liquid, this is melting point. That's a straight line because it's at this temperature melt. And this is temperature boil, right? So if we are going from, we're putting heat into ice to change it into a liquid, we're changing the temperature. We have to take into account temperature change within the same phase, right? Plus the phase change, which is here. So that is very important. And you'll kind of figure that out as we answer the homeworks. So, but for now, just know that in calorimetry, the sum of all heat transfer is 0, and this consists of two things, right? temperature change within the same phase, which is equal to mass times specific heat times change in temperature. Also, the heat transfer necessary to change phase, which is plus or minus mass times latent heat of either fusion or latent heat of vaporization, depending on what phase we're going to or switching from. So yeah, that's just a quick summary of important formulas and terms in chapter 17, temperature and heat. Okay, hope that helps.